Guys, can you see this board?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So today we shall discuss physical meaning or physical interpretation of gradient. Okay. Let us say we have some scalar function f x and y. We keep it only in 2 dimensions, and let us keep it as simple as possible. So I take f xy as product of x and y. So what does this function look like? Let us plot this function. So we have one x-axis, let us say this, one y-axis, this is y, and what we are going to plot is fx comma y, which is actually xy in this example, is equal to some constant. Okay. So let us say this constant is 1, then what we are going to plot is xy is equal to 1 or y is equal to 1 upon x. So this should look like something like this. At x is equal to 0, y is infinity, and as x increases, y decrease. So the plot is like this. Now if we choose 2 here, then this is 2, we get another curve. That curve is something like, the structure remains same, although it is, if you plot, it will be on the right hand side. If you take 3, you will get another curve. Okay. So for this curve, f is equal to 1. I mean, anywhere on this curve, if you calculate f, it will be 1. On this curve, f is equal to 2. On this curve, it is 3, and so on. Okay. So let me plot exact curve, many curves like this. So let me use some software for this. Okay, so this is the precise curve. This is x-axis. Let me explain how do we get curve here. This is x-axis. This is y-axis, and each color represent a value. So as you can see, for this curve, let us say for this curve, xy is equal to 1.
Sir, your screen got freeze, sir.
Sir, you are not audible.
Can you see this board?
Yes.
Okay, sorry. There was net. So this is a color plot, means whenever xy changes its value, the color will also change. And for some particular color, there are lines. Okay. So as you can see, the whatever color is here, same color is here also. So whatever is the value of xy here, same value of xy is here. So for this line also, xy is equal to 1. Here x and y both are positive. That's why product is positive. In this side, x is negative as well as y is negative. This is xy is equal to 2, xy is equal to 3. And here you can see other colors. Why? Because here xy is -1, it is -2, it is -3 now, -4, and same on this side. Now let us calculate gradient of this function. So what I'm going to calculate is gradient of xy, and this is equal to what we get. Let us see what is the form of this gradient. So this is gradient, right? On x-axis means y is equal to 0. Gradient is this. So when on x-axis y is equal to 0, gradient is xj cap. Means if x is positive, it is pointing up. If x is negative, it is pointing down. So gradient look like this at x is equal to 0. At y is equal to 0 means x-axis. When x is negative, it is pointing down j cap like this. Okay. On y-axis, y-axis means x is equal to 0. Gradient is y I cap. So if you are on the positive side, y I cap. Here y is positive, so it is in this direction. Here it is on this direction. Okay. Let us focus on this point. So at this point, x is small and y is large. Let us write here. X is small here, right? And y is large. What is gradient? Gradient is y I cap x j cap. So y is large means I component is bigger than the horizontal component is bigger than vertical component. Horizontal component is bigger. It means it is like in this direction, right? So that horizontal component is larger than the vertical component. What about this point? X is large, y is small. Y small means horizontal component is small, vertical component is large. So gradient is in this direction here. Similarly, you can check at all other directions. It behave like this. Okay. Now what actually is this angle? जो constant functions के curve हैं, at this curve function remain constant, and this is the direction of gradient. What is this angle? So in order to find this angle, let us find some more properties of gradient. Let us calculate change in function. When we go from one point to other, means if we are here, if we are at this point, the value of function is 1. If we are at this point, value of function is 2. If we are somewhere between, value of function may be 1.5 or 1.7, right? So let us calculate, let us count, if we move it distance by dr, how much is the change in the function? यदि हम एक थोड़ा सा डिस्टेंस ट्रेवल करेंगे तो फंक्शन में कितना चेंज आएगा? The change is delta f. How much it is? This much, right? Just guys give me 1 minute. It means if you go delta x along the horizontal direction and delta y along the vertical direction, then this much is the change in the function. I am going to write it like this. Okay, or this is actually equal to the gradient of this function dot product with the displacement that you do. So this is the change in the function. Now let us try to answer some questions. Which directions show maximum change in f? So how do I find the direction where I will receive maximum change in the function? Any answer?
Theta 0, sir.
Sorry?
So when they are in
Sir, it is a
parallel.
dot product.
When we see, so this is actually equal to del f mod delta r mod times cos theta. Theta is the angle between these two. See, this is a fixed vector, right? Because it all depends on function. This is the direction chosen by you. Now, if both the directions are same, theta is 0 and delta f is maximum. What does it mean? Let us say we are here. We are at this point. The gradient is in this direction. Okay. Now let us say delta R mode is 1 mm. But you can move in any direction. You can move here 1 mm. You can move in this direction also by 1 mm. You can move in this direction, this direction, this direction. But you can see if you go along this direction, there is no change in the function. It was 1 here, it is 1 here also. The change is 0. In this direction, there is a change. In this direction, there is a change, but the change is quite small. In this direction, the change is maximum. In this direction, also change is quite small. So, what is the direction in which it will give you maximum change? The direction
In the
which is
direction of
the
gradient.
direction of del f, right? So, this is the direction of maximum change. If this is the direction of del f, you should go in this direction to receive the maximum change. So let us write it in words also. In the direction of del f. How much is the change? How much is the rate of change? The magnitude of this. Right? Next question is obviously, which directions show minimum change?
Sir, perpendicular, sir.
Right. Because for minimum change, so this is delta f. It is obviously this. So if angle between these two is 90 degree, if delta f is perpendicular to delta r, how much is the change? Delta f is obviously 0, right? Means if you go along perpendicular direction, either in this side or in this side, there is minimum change, and that change is 0. But 0 means what? Function remain constant along these directions. Or we can say that gradient is always perpendicular to the surface of constant value, right? So what is the first property of gradient? Surface or curve. In 2D it is curve, in 3D it becomes surface. Curve of constant values. Okay. So this is one very basic property of gradient. It always shows you the direction which is perpendicular to the equipotential or equal value surfaces. Let us say F represents potential. Okay. Then what does it represent? A direction which is perpendicular to the equipotential surfaces. What is the physical meaning of this? So let me give you some very basic and very, physics related example. This is Earth, right? Let us say we have some gravitational potential here at some height h. How much it is? mgh, right? Here also we have height h, same height. Potential here also is mgh, right? So if we draw a curve of equipotential point, यदि हम ऐसे सारे पॉइंट्स को जोड़ लें जिन पे सेम पोटेंशियल है, we get a surface like this, right? What is the potential here? B is equal to B1 is equal to mgh or mgh1. Similarly for all these points, V is equal to B2 is equal to mgh2. Okay. What is the direction of force at this point? It is in this direction, right?
Into.
What is the direction of force at this point?
Towards the core.
Towards the core, or actually that is why it is also perpendicular to the equipotential surfaces, right? So if V represents potential, what do you see? Gradient of V represents what?
Sir, electric field.
Electric or gravitational, whatever, right? So this is the one of the very beautiful use of gradient. It helps you recognize force for the cases where you can define the potential. यदि आप कहीं potential define करते हैं, just take the gradient of that potential and you will get the corresponding force at a point. Okay. Can you think of any other benefit of gradient?
सर अगर दो प्लेन के बीच एंगल फाइंड आउट करना होता है तो ग्रेडियंट का यूज करते हैं।
How do you find angle between two planes?
सर पहले ग्रेडियंट फाइंड आउट करेंगे, फिर डॉट प्रोडक्ट ले लेंगे, उसके बाद निकाल लेंगे।
Give me some, I mean, I have doubt in your argument. Let us say we have one plane like this, okay, and let us say we have other plane like this. It is passing through the, then how do you find angle between two planes? आप कैसे angle पता करेंगे? Okay, all right. So you are trying to find perpendicular to this plane, perpendicular to other plane, and then take the dot product, right?
Yes sir.
Yes, that is also one good example. So you can use gradient for these cases. And I'll also introduce one more example after a short while. Now let me discuss some benefit of divergence. And the name is also quite intuitive. It calculates the capability or the effect of a flow which is
Sir, you are not audible.
Yes sir.
हमारी नहीं आ रही।
yes. Can you see this board?
Yes, sir.
Okay, good. So it calculates how much things are diverging out. So let us consider some physical example of this. Let us say it is a sink, okay, or let us say it is a garden, and there is a water tap here. So since this is a water source, water will obviously come out from this source, will go in all directions. Okay. And then it will flow everywhere. It will start moving on its own. It will go everywhere in this garden, right? Let us focus on a small area here. Whatever is the water coming into this area, obviously if there is nothing here, similar amount of water will go out from this area. यदि एक छोटा सा आप जमीन का टुकड़ा यहाँ लेते हैं, and let us say there is no absorption of water, इस जमीन के टुकड़े ने खुद से कोई पानी एब्जॉर्ब नहीं किया है, देन जितना भी पानी और जितना भी वाटर फ्लो इस जमीन के टुकड़े में आ रहा है, एंटरिंग, exactly same amount of water is going out through the same piece of land, right? Or in mathematical word, we say that divergence is zero. There is no effective divergence. जितना फ्लो आ रहा था, जितना फ्लक्स आ रहा है, similar amount of flux is getting out. What about at this point? I mean, let us say we take a small area which contains the water source. Now, how much water is flowing in? कितना वाटर अंदर आ रहा है इसमें? Nothing. Flowing out? Obviously something, right? So for this reason, divergence is greater than zero. Now let us say we have some hole somewhere in the ground. Let us say here. So whatever water goes in this direction, that will enter into this hole and then it will disappear. So if we take a small area around this hole, what do you see? There is a water flowing into this area. Okay. Some of the water gets into hole, some of the water may get out. Okay. So for this case, flowing in, yes, something कुछ तो है. Flowing out, maybe some water, but flowing out water is obviously less than in. जितना पानी बाहर जा रहा है उससे कहीं गुना पानी अंदर आ रहा है, and obviously जो भी difference है that is going into this hole. So here water is shrinking, coming into one place, and for these cases we say that divergence is less than zero. Okay. Now why do we say all these definitions for divergence? कैसे पता चला कि divergence zero का इस cases में? So let us calculate the flow for all these three cases, and you will see that the quantity that defines this behavior is actually divergence. So we are going to consider a very simple case is that water is flowing on a field in all directions. Okay. Well, let us consider in 2 dimensions so that we can draw geometrical graph very easily. So at any point P, let us say velocity is this, xy. Okay. And as we go a little bit further, Let us say velocity here is this. Okay. So this is the field. Okay. I am considering this small element here, delta x, delta y. The water is going into this area and water is also getting out through this area. Okay. I want to know how much water is going in. So let us say the water that is going in has the velocity v xy, and the water that is going out has the velocity now so what is the input flux? Kitna flux? So let us write it like the x component of this velocity that may depend on both I cap plus y component of the velocity that may also depends on x by j cap. So x component means this, y component means this. What is the input flux? So x component is this. Corresponding flux is डेल्टा वाई लेंथ से कितना फ्लूइड अंदर गया वी एक्स डेल्टा वाई एंड वाई कंपोनेंट इज गोइंग इन दिस इस डायरेक्शन से कितना फ्लूइड इस एरिया में अंदर गया बी वाई डेल्टा एक्स राइट One minute, there is a problem. I think something, just 1 minute, there is one problem here. This is xy, this is x plus delta x. This is xy plus delta y. This has to be vx delta y plus natural less. But here in this direction, it is, this is also okay. But then Okay, right. Yes, yes. Okay, let's continue. I think calculations are right. Let us see. So this is the input flux. Any doubt with this part?
Sir,
Yes.
sir, flux is not V bar dot dA bar into n cap.
So flux means what? What is the definition of flux? Huh?
Sir, something amount of any vector field going inside or
Right.
getting outside closed area for a
So
closed area.
let us say this is a line, okay, and a vector field is going from this direction. The length of this line is delta y, and let us say this is a constant vector, vector v. Vector v is this vx I cap plus by j cap. So how much is the flux passing through this window? Vector v dot delta y, right?
Yes, sir.
Delta y. What is the direction of delta y?
Perpendicular to the area.
This, right, means I cap, right? What is the flux? The dot product becomes bx delta y. I dot I is 1 and there is nothing. J dot I is 0, right? So same thing I'm writing here. Vx delta y. Similarly from
Yes,
this
sir.
side,
Understood, sir.
by delta x. Okay. Actually, that was I was thinking because I got confused whether I'm writing it correctly or not. But anyway. So whenever we write in shortcut without thinking much, we always get confused. Anyway. What about this? This is the velocity field at the other side here. After traveling delta x distance along the horizontal and after traveling delta y distance along the vertical. So first of all, let us express this. So velocity here can be written as vx, and I hope you are aware of the Taylor extension. So I can write this vector as vx plus del v over del x delta x plus del v over del y delta y, and plus there are other term. So, this is actually vector v is bx x plus delta x y plus delta y I cap plus by j cap, right? Now let us do the Taylor expansion. This can be written as bx at x plus del v over del x delta x plus del v x over del y delta y plus times I cap, right? Similarly for j cap, vy at the point xy at the point xy plus del vy over del x delta x plus del by over del y delta y. Okay. What is the outgoing flux? Outgoing flux कितना होगा? Multiply I cap component with delta y, multiply j cap component with delta x. How much it is? Vx. Now I'm going to drop this xy in bracket. delta y, multiply delta y with this. This is what? Vy delta x square, delta y delta x. So what is the net outgoing flux? This is the outgoing flux from the right hand side, and this is the incoming flux from the left hand side. How much is the net flow?
Difference between outgoing and income.
Net flow is, so this quantity minus the previous quantity. So this cancels. What we are left with? Are we making some mistake somewhere? This flow may depends on both. If you go along y also, the flow may increase. There is no doubt here. This flow can also increase. Accordingly, del Vx upon del y may survive. No, but del Vx upon del y is this. So incoming flow is also increasing then. And this is also not right.
Sir, what is the area vector? It is del x I cap plus del y j cap, or the reverse?
You mean the area vector of this enclosing area?
Yes, sir.
We do not need that area. Just give me some time. There is some. I mean, no. I'm getting what is the problem, but can I avoid that problem? If I assume that Vx increase along y, I can assume there is no loss of generalization if I assume that. But then why I'm getting less contribution? Although the order is same, and if I further shrink it to the source, But obviously there is a component here also. It has to be Vx del Vx over del y, and it is delta y, which is the same term which is like this. It is Vxy. And this is V x plus delta x, y plus delta y. This is V x plus delta x and y. So what is the flux that is getting out from this side? The flux that is getting out from this side is how much? Flux out is actually vector V x plus delta x y into delta y and integral y to y plus delta y. So that's why it, okay. Or we can keep it simple. Vector V here, xy. So there is a, it's not a problem, but the way I am doing, it is going to be very mathematical. Actually, this part is not right. Do you know why? This part is incorrect. This is not the input flux. कोई बता सकता है क्या हो रहा है? Right. If you see very carefully, let me make a enlarged version of this small area. This is the point xy. This is x plus delta x y. This is x y plus delta y. And this is obviously x plus delta x and y plus delta y. In this small area here, the input flux is Vx dy. But here in this small area, input flux is not same. It is how much? The x component has now increased. let us say it becomes Vx prime, then it is Vx prime delta y. Whereas what we have considered that Vx vector remains same along this whole y direction. हमने ये मान लेते कि जो Vx यहाँ पर है वही Vx यहाँ पर भी है. But that may not be true in general. In general ये सही नहीं हो सकता. या तो हम ये माने. So how do we make it correct?
सर इसको दो पार्ट में कर लेते हैं.
See, so why it is not correct? How to make it correct? यदि हम इसको input flux कह रहे हैं, it means Vx is a function of x only, right? We cannot assume Vx is a function of y, and here Vy is a function of y only. We cannot assume it as a function of x. And if we consider it as a function of x and y both, तब ये सही नहीं होगा. Then we will have to integrate it over the whole length. So it will give you some extra terms. So let us keep it simple. And how to make it simple? We will discuss this part if we get time. But for now, let us keep it simple. So what I'm going to do, let us assume x component is free from y and y component is free from x. Okay. Now this is acceptable. And please don't worry if you don't get it. We will rediscuss it in the next class. Although I'm not left with much time. इसको हम कल फिर से डिस्कस कर सकते हैं क्लास में. So don't worry about it if you don't get it. So if this is an input flux, we are actually assuming that x component is function of x only, y component is function of y only. This means this term will not be there, and this term will also not be there. Okay. So what is the net outgoing flux? Remove this term and remove this term also. And what we are left with is delta x, delta y. Or I can write this thing as divergence of B into delta x, delta y. So you can see if there is a net flow, I mean if there is a source inside it, when you will get net outgoing, आप किस केस में net outgoing flow पाएंगे? When less water get into and more water come out. इसका क्या मतलब हुआ? There is a source inside this area, right? And when this happens, net flow is positive. It means this part has to be positive. This is obviously positive. This cannot be zero. Similarly, if net flow is negative, negative means more water come in but less water come out. It means there is a sink which is diverting water to some other location. In that case, net flow is negative, divergence is also negative. And if there is nothing inside this area, whatever water gets in, similar amount of water gets out. And in that case, this quantity will be 0. Okay. So divergence or del dot B or del dot F is a measure of flow. It finds source and sink of flow. Source and sink of flow means, so let me give you one real life example here. Let us say this is a charge Q. So this is the source. Source of what? Electric field. Right? Electric field is being generated from here. यहाँ से electric field produce हो रहा है. Electric field is here also. यहाँ पे भी electric field है because of this charge. So if you take any small area in this region, whatever is the flux getting in, जितना ही flux अंदर आ रहा है, similar amount of flux is getting out. So for this area, del dot E is 0. Divergence of electric field is 0. But if you calculate divergence of electric field around this charge, then what will happen? Now it is not 0. कितना होगा, that is another problem, but it cannot be 0. But वो 0 नहीं हो सकता. Similarly, if there is a negative charge at this point, it is capturing the electric field. Electric field is coming towards it. If you take a small area around this charge, there is a net inside flow of electric field. यहाँ पे जितना भी फ्लो है सब अंदर को आ रहा है. There is no outgoing flow. So in this case, del dot E is less than 0. It is greater than 0 here. And at any other point जहाँ पे चार्ज नहीं है, let us say this point, whether charge यहाँ पे प्लस या माइनस does not matter. Del dot E has to be 0. Okay. So this is the benefit of divergence. It helps you to find presence of sources. यदि source या sink होगा, then only there is a change in the flow. Otherwise, flow always remains same. So let's stop here. You may have some doubt that we will clear in the next class. If you have any small doubt, you can ask now. Okay, so let's end this class. Take the attendance. Yes.